Okay, so I'm now going to go through 5.2, which is covalent bonding. Okay, so let's share the screen, which is there. Okay, so obviously we're moving our homework onto Teams, back onto Teams. Remember that we have extra support sessions. Right, so what you need to do is start by thinking about some dot and cross diagrams. You could have a go at that. You could stop the video if you need to. But if you're happy with that, we'll just move on. Okay, so trying to draw a magnesium hydroxide is a bit more of a challenge because we've got a compound ion there, the hydroxide. Okay, so let's move on. Okay, so this is what we're going to look at here. We looked at ionic bonding last time and giant ionic lattices. We're now going to look at covalent bonding, having a look at multiple covalent bonds, drawing dot and cross diagrams. We'll also look at this new type of bonding called dative covalent or coordinate bonding, and we'll be still able to use dot and cross diagrams. And we can sort of use the bond enthalpy, which is a measurement of the strength of a bond. And we talk about the average bond enthalpy of a covalent bond. And we should, well, hopefully everybody should be able to look at joint molecular ions. We'll also be looking at some substances that do not complete what we call the octet, okay, or actually over-complete the octet, so we'll look at that. They're the key words, okay? The definitions are here, okay? So obviously you should make yourself some flashcards, make sure you learn them. Okay, so covalent compounds. What species form covalent compounds? It's usually a combination of non-metals. Okay, why are they bonding? They want to get a full outer shell. Okay, as the atoms come near their outer electrons, attract to the nucleus of both atoms and become shared. So what we could do if I shift to a different screen, in fact, we'll put this here and we'll bring that up onto here in the visualizer. Okay, what we can think about is that if we have a positive nucleus there and another positive nucleus here from two non-metal atoms, what happens is if they're going to share the electrons, so let's put an electron here and another electron here, what we can think about is that, well, these two nuclei are going to try and repel each other, okay, but they're going to be attracted towards that electron, okay, and the other nucleus is also going to be attracted to those electrons if we put them in between. So this is two electrons, which would make a single bond, and eventually we'll get to a point where we have resultant forces where this has a component pushing it that way, this has a component pushing it that way, that has a component pushing it that way, that has a component pushing it that way, and then this repulsion force and these attractive forces get to an even point, and we then end up with these two nuclei held together in a bond of a set length. So we might have so this has a bond length, okay, and it would have a bond enthalpy. Okay, so it has a bond length and a bond enthalpy. Okay, so let's move this out of the way. Okay, so they're sharing the electrons there. And then the electrons then count towards both shells of both atoms that are being shared. So we have the example here, and we can draw it like that. I would suggest, though, that a better way of drawing the bond sharing, if I can bring my other slides back up again, okay, is to draw the sharing by overlapping, and then put the electrons inside the overlap like that. It's much clearer. It ends up being less messy than when it's on the actual lines. Okay. Right. Okay. So we've got it's localized. It's acting between the two bonded atoms, and they're sharing a pair of electrons between their nuclei. And there's a way of drawing like that. Okay. So some compounds actually share 4 electrons or even 6, okay? And that obviously gives rise to single, double, and triple covalent bonds. Later, we'll see why, when we start to look at organic chemistry, we'll see why we can't have them sharing 8. In other words, having a quadruple bond. We can only have single, double, or triple bonds. It's about spatial arrangement and repulsion. We can't get a quadruple bond. So, for example, there's a single bond, chlorine-chlorine. There's a double bond, oxygen. There is a nitrogen triple bond. Okay. So there are questions on page 18 of the booklet. Okay, you should be able to have a go at some of those. Most, there were ionic ones and there's some covalent ones. Okay, so we'll go through these questions now. And here we've got the SPTF electronic configuration notification notation. So we've got two chlorines coming together. Their SPDF notification means that they are 3p5 at the end. It means they need to gain another electron. And when they share, they each think they've now got 3p6. Okay, and here we've got them overlapping and sharing their electrons. And that's, hence that's why we use dotting crosses, so we can try and represent which electron comes from which atom. Electrons don't actually really care who they belong to, okay, as such. But it's just for our visualization, so we can sort of try to understand it. That's our chlorine-chlorine bond. Okay, question 2 is F2, fairly straightforward. Oxygen is SP2p4, okay, so it needs 2 more electrons. So here we're going to make a double bond, and there we've got 4 electrons in the overlap, okay. Hydrogen needs 1 more electron, so nitrogen, how many more nitrogen need? It's 2p3. Yep, that's right, it needs 3. So how many hydrogens would you need to share with the nitrogen? You're going to need 3 hydrogens, because a hydrogen only needs to share 1, but nitrogen needs 3. Therefore, the bonding in ammonia looks like this. There's the separate atoms, and they come together like that. And interestingly, because nitrogen's got 5 electrons in its outer shell, we've got a lone pair of electrons sticking out the top. And when we come on to topic chapter 6, that will help. That will lead to us talking about shapes of molecules. Okay, so that has a lone pair, 2 electrons at the top here, which are not involved in bonding. Okay, hydrogen iodide, straightforward. Okay, carbon dioxide. Now this here we've got our carbon having 4 electrons, so it's 2p2. Okay, well, it's 2s2 2p2, so it's got the 4 electrons, and the oxygen will come and share. So we have 2 double bonds. Yeah, so we've got 2 double bonds, and there we've got the 4 electrons in each overlap in each double bond. So it's CO2. Right, hydrogen peroxide. Hydrogen peroxide is interesting because, remember, we talked about oxidation numbers. This gives us oxygen with a non-standard oxidation number. It means that the oxygen is -1, not -2 in its oxidation number. That was chapter 4. So here, what we have is the hydrogens will overlap with 1 oxygen each, and the oxygens will overlap with an oxygen each. Okay, and that's how we end up with hydrogen peroxide. H2O2. Okay, and how many, so then we have some lone pairs. Okay, how many lone pairs have we got? Well, we've got a lone pair here, a lone pair here, a lone pair here, a lone pair here. Okay, so those are pairs of electrons, are not bonding. So there are, in fact, 4 lone pairs, 1, 2, 3, 4. Okay, sulfur trioxide. Now, this is a little bit more tricky because there are 2 possible ways of doing it. We could have an oxygen making a double bond with the sulfur. That's all good. Now those 2 oxygens now both think they've got 6. The sulfur now thinks it's got 8. But there's still a pair of electrons here. Okay, and the sulfur could make actually, so count up those electrons. 4, 8, 12. Sulfur is a bit odd. Sulfur, well, it's not that odd, but sulfur can actually expand the octet. It can actually have more than 8 in its outer shell. Okay, and so therefore we've got 3 double bonds with the oxygen. Alternatively, you could do this. Okay, and here the oxygen is actually taking both electrons. So it's only a single bond there and a single bond there and a double bond here. Okay, so that's 4 electrons shared with the sulfur. And the sulfur here is actually being very generous and giving both its electrons to the oxygen. That's what we would call a dative or a coordinate bond. Okay. So now, okay, we've got some covalent bonds. Now we can actually then think about, well, how do we get ionic compounds that are molecular ions? So we've got hydroxide, nitrate, that's nitrate 5, got sulfate 6, carbonate, phosphate, and ammonium. Okay, all of those are ions that you need to know, okay, what their charges are and what their chemical formulae are. So they can form ionic bonds with other ions, but let's have a look at how we would draw that out. So ammonium, okay, it's got hydrogen, 4 hydrogens around the nitrogen. And here again, we've got nitrogen sharing both of its electrons with hydrogen. This hydrogen's got no electrons, so we've got a deficit of electrons compared to protons, and therefore this ammonium is +1. Okay, so here is our ammonium ion. So that means it would basically, the hydrogen has given away, or this molecular ion has given away 1 electron to the chlorine to make it chloride, and they're now going to stick together, but as an ion. But notice this is the covalent molecular ion, but we have drawn it in square brackets because it's now an ion. It must be square brackets, so make sure you're very clear about that. There's no overlap between the ammonium and the chloride. Okay, so some of you can just carry on working through the questions because you should be able to get on with that. Okay, now sulfate 6. Okay, this is a bit more tricky. Okay, you've got 4 oxygens, okay, and it's 2 minus overall, okay. So that means that basically the oxygen has got an extra electron from the hydrogen, okay. So that's those crosses there. 1 cross there is an extra electron, 1 cross there is an extra electron. That means it's 2 minus overall. And if we have a look at this, we've got a double bond here, so 2 electrons from the oxygen, 2 electrons from the sulfur. Same over here. And then we've got 1 electron from the oxygen, 1 from the sulfur to give us single bonds here, and that's its structure. Okay, and the sulfur has expanded its octet. Okay, and on the other side we've got nitrate, nitrate and 5. Okay, again we've got a coordinate bond or a dative bond. That's the one where both electrons come from 1 atom or species. We can call these species sometimes. So that's 1 atom. Has shared both electrons there. It's got a double bond, okay, it's got a single bond, which is dative, it's got another bond there. And this is negative overall because it has grabbed an electron. This green one represents electrons come from somewhere else. Okay, and then we can also have a look at carbonate. Here's carbonate, okay, we've got 4, carbon's got 8 electrons, that's happy. Nitrogen's got 8 electrons. I'm just going to turn my phone off. It seems to have opened up Google for some unknown reason. Okay, so this is the carbonate ion, and again we've got an extra electron that's come from somewhere else on both of these oxygens, and therefore it is 2 minus overall. And we would draw it in square brackets because it's an ion. Okay, so for combining hydroxide and calcium, calcium is 2 plus. Notice here there's a big 2 outside this bracket. I need 2 OHs. And again, that green electron, that is the one that's come from calcium. But calcium needs to give away 2, so I need 2 hydroxides. Each one has got 1 electron, that green triangle from calcium. You can use any sort of symbol you like for representing them, but try to obviously the oxygen electrons are the blue ones. That's the original 6 electrons in its outer shell. That red one is the 1 in the outer shell of hydrogen, and this green one is the one that's come from calcium. Okay, and there's 2 of these hydroxides. Cyanide is a molecular ion. It's this, and you can see that the carbon has got an extra electron. It's the carbon, it's the negative side. It's also got a triple bond. Okay, so hopefully you should be able to work that out. In fact, if you haven't done it, stop the video now, and then I'll draw it onto the visualizer. Okay, So let's draw it onto the visualizer. Okay, so we have got C triple bond nitrogen, and the carbon is negative. Oops. So let's rub this out. Okay, so we're going to put, so carbon has got 4 of its own electrons, 1, 2, 3, and 4. Okay, nitrogen has got 5 of its own electrons, so there's 1, 2, 3, so there's 3 crosses. Let's make this bigger. Let's see it properly. Up. So we've got 1, 2, 3. There's the nitrogen ones. Carbon's got 1 electron left over. So we've got 3 there. We've got another 2. We'll use crosses for the nitrogen. There's the nitrogen, there's the carbon. Okay, so there's our triple bond. Okay, here and here and here. Yeah, with 6 electrons in the middle. 6 E minus there. And then this must have an electron from somewhere else, which will make it negative. Yeah, that's better. And so this makes this negative overall. So I'll put a minus sign up there. This electron is from somewhere else. Which could be, if it's CN, this is CN, it could be hydrogen. Yeah, so then we would have HCN. Okay. That out of the way. Okay, so how many covalent bonds? So we now know that carbon, because it's got 4 electrons out of shell, makes 4 bonds. Nitrogen has got 5 electrons out of shell, so it needs another 3. So it makes 3 bonds. Oxygen's got 6 in its outer shell, needs another 2, so it makes 2 bonds, and hydrogen makes 1. Okay, they're trying to get a noble gas. Okay, but sometimes there's not enough electrons to fill the outer shell. Okay, and or sometimes more than 4 electrons may pair up, where we might end up with more than 8 in the outer shell. So not enough electrons. Right, beryllium, boron, and potentially aluminium can form covalent compounds. Now you'd expect beryllium to be an ionic, it is a metal, but you'd expect it to behave like a metal and form Be2+ ions. But it doesn't. It actually does covalent bonding instead of making ionic bonds. And because it's got 2 electrons in its outer shell, it can only make 2 pairs of bonds. So it ends up only having 4 in its outer shell. So that is beryllium chloride, BeCl2. In terms of its formula, it looks like it's ionic, BeCl2, but it's actually covalent. Okay, and boron, okay, has got 3 electrons out of shell, and therefore it doesn't form B3+. It will make BF3, which does look like it's ionic, okay, because it looks as though boron should be 3+, but actually it doesn't do that. And we need to think about why that is. Okay, and it's pretty simple. Well, I think it's relatively simple. Beryllium and boron are both very small, in the second period, very small atoms. And the nuclear charge, well, beryllium has got 4 electrons, it's got 4 protons, and those 4 protons pull those electrons really firmly in, and therefore it's very, very hard to ionize beryllium. Okay, so it's hard for it to actually lose those electrons. Okay, so it's trying to lose them and then pulls them back in again because of the nucleus being so strong. Now, boron is not much bigger at all. It's the next element along, and it's got 5 protons, so it's even stronger with its nuclear force. So it pulls them back in and doesn't let them go. So it's like it's trying to be ionic, but it doesn't do it. Okay, and so it forms they form covalent bonds, and they have not completed the octet. Okay, now there are some elements that actually do more than that, as you've seen already. These start in period 3. So it's like sulfur, sulfur, phosphorus, and chlorine can all expand their octet, and they can have more than 8. Atoms of non-metal in group 15 form 3 or 5 bonds, depending on how many electrons are in the bonding. This is group 5 or group 15. Yeah, so this can be called group 5 or group 15 in the expanded table. So group 5 or group 15 can form 3 or 5. Okay, depends on how many electrons are used in the bonding. Group 16 can do 2, 4, or 6. Okay, up to 6. How many electrons does sulfur have in its outer shell? 6. So it can form up to 6 pairs. Okay, so 6 bonds. And group 7, yeah, you guessed it, can do 1, 3, 5, or 7. Okay, because they can either bond the 1 electron that they haven't, that's not paired up, or they could bond 3. Okay, so it has to be an odd number there. Or they can go up to 7 because they've got 7 electrons in their outer shell, and that will happen for arsenic, selenium, bromine, tellurium, iodine, and astatine as well. Okay, that's in your textbook if you want to look at that further. So how are they going to do it? So here's an example. Okay, so well, they're in the 3rd period, and you now know that period 3 can contain up to 18 electrons. Okay, so here is sulfur. This is sulfur hexafluoride. So it's got 6 fluorines around it. Each fluorine is giving 1. Each sulfur's got 6. So you've got 6 pairs of electrons making 6 bonds, and then the sulfur therefore has got 12 electrons in the outer shell. Okay, once it's bonded. Okay, and it's happy like that. Okay, because it's got no unpaired electrons. So a better rule about making covalent bonds is that any unpaired electron can pair up. Okay, and the maximum number is going to be equivalent to the total number of electrons in the outer shell. Okay, so we talked about dative or coordinate bonds earlier. Okay, it's overlapping of an empty orbital of an atom with an orbital, like for instance, oxygen's got 6 electrons. They could be forced to pair up. Okay, so we've got 3 pairs, and then there's space for another pair. And then that comes from a lone pair, a pair that hasn't bonded, from another atom. So we have a donor and acceptor atom. Okay, it's just a normal bond. Okay, we're calling it a dative or a coordinate bond is just so that we know that it's come from one atom, but it's just an ordinary bond. Okay, but you can show it in your Don-Cross diagram. So for instance, how we formed ammonium is the fact we've got ammonia, the nitrogen's got a lone pair, we've got a hydrogen ion, which has got no electrons, and so the nitrogen can donate the pair here. Yeah, so that's our dative bond or a coordinate bond. It's got 2 names. It's called a coordinate bond. When we come on to look at transition metal, that makes more sense why it's called a coordinate bond as well. And we can show it like this. Now, what we often do is we show that bond line with an arrow showing that the electrons have come from the nitrogen and going to the hydrogen. Okay, the same thing happens in water. Now, I said earlier when we looked at acid and base that actually H plus is not really the case. We can't really have protons going around separately. They actually join to a water molecule to make H3O plus. Okay, so when we remember that hydrogen is not really hydrogen ions, it's actually the hydroxonium ion. And that's done in the same way. We've got a dative bond here. This hydrogen, this proton, which can't really go around by itself, is joined to the oxygen with one of the pairs of, or one of the lone pairs from the oxygen. So that's the dative bond there. Yeah, okay. So now have a go at see if you can link ammonia and boron trifluoride together and see how they work together. So now you should stop the video, have a go yourself, and when you've done it, come back. Okay, so here we go. Here is our ammonia. Here is our boron trifluoride, which, as you know, or as you saw earlier, has not completed the octet. It's got an orbital spare. Okay, the ammonia has got a lone pair, And so that lone pair can go in there and form that together. And we can represent that with dot and cross, as shown here. Or we can just draw the bond lines out and show this lone pair has been donated towards the boron. And we have a dative bond here. Okay, so aluminium chloride, as I said, aluminium sometimes doesn't form, especially with chlorine, because the size of the ions works out quite nicely. Doesn't actually form ionic compounds. It forms covalent compounds with chlorine. So aluminium has got 3 electrons, so it makes 3 bonds, okay, with chlorine. Chlorine, that makes the chlorine happy. Chlorine's now got 8. The aluminium has not completed the octet. Okay, so it's quite possible, I hope you can see, that this chlorine has got a lone pair. Okay, so if you had another aluminium chloride, it could come along and join with it, and therefore we have what's called a dimer. Mer means part, di obviously 2, so it's made of 2 parts. It's made of 2 of these. Okay, and again, aluminium is still pretty small, and to make it 3+ is going to be pretty hard. Okay. So it needs a high ionization energy. So if we look at the dimer, here you can see we've got 1 aluminium chloride here, and they can overlap. The lone pair from this chlorine can fill that aluminium's spare orbital, and the lone pair from this chlorine can fill this aluminium's spare orbital. And so we've got that, and we can draw it like this, showing that that's the lone pair going from the chlorine to the aluminium, and from that chlorine to that aluminium. Okay. So that's, dimer. So now we can look at average bond enthalpies. Average enthalpies take place when breaking a mole of a given bond in molecules of gaseous species. So if I take hydrogen as a gas, I can break the bond, and I need 436 kilojoules per mole to break that bond. And you can see some of those energies. So it uses the measurement of bond strength. Okay, and the higher the bond enthalpy, the more energy it takes to break the bond, so the stronger the bond. Which is the strongest bond there? Okay, think about it. It's the carbon monoxide. That's got a carbon-oxygen triple bond. Okay, 1074. Nitrogen is also a triple bond, also very high. Oxygen, quite high. It's a double bond. Fluorine low, it's only single. Chlorine's only single. Bromine is single. Iodine, single. HF is a single bond, but there's a lot of energy in it because of the fluorine. Okay, so there's a difference between these two. Okay, and they're very small. Fluorine's very small, so it can pull the electrons towards it quite strongly. And you can see there is, so the reason these have been put up, HF, HCl, HBr, and HI, you can see that it's a decreasing bond enthalpy. The hydrogen and fluorine will stick together really strongly, more strongly than HCl, which is more strong than HBr. So there's a trend as you go down the table. Okay, and that's related to the size of these atoms. Okay, and fluorine being smaller than chlorine, chlorine being smaller than bromine, etc. Okay, so in summary, carbon, nitrogen, oxygen almost always fill their outer shell. Okay, they will have 8 electrons in their outer shell. Okay, beryllium, boron, aluminium often do not. The second row never exceed 8. Okay, period 2. Period 3 can, and they can exceed the 8 up to their final number of electrons in their shell. So, for instance, the group 7s can add up to 7, so they could actually have 7 bonds. So that is a possibility. Okay, now there are some questions there. Okay, to have a go at and make sure you understand. Obviously, the red stuff, everybody should be able to do the red stuff. The majority should be able to do the orange stuff. And the green stuff is the stuff that if you're working towards A&A star, you should be going for. Okay, so this is, you may want to stop the video as you go through that. Okay, and then you can see that's what we have covered. Okay. So you may be able to explain it to somebody else. Explaining it to somebody else is always a good thing. Okay. Let's see if I can finish